Hey guys, welcome to another lecture video for Chem 115. In this video, you will learn how to qualitatively predict if the ions of soluble salts affect the pH of the solution. We're going to go ahead and extend this concept one step further, and we're going to learn how to quantify that pH. So before we get started, I want to go ahead and flash on the screen a couple of the foundational concepts that we learned in part 1 of this lecture video series. And so the first thing that I want to flash is the list of common strong bases and the list of common strong acids. So if you haven't done so in the previous video, go ahead and take a quick snapshot or pause the video and write this down on your notes just so that you have it for your reference. The second item that I want to flash are the rules that helped us predict whether or not the ions of an ionic compound, when it's dissolved in water, will change the pH of that solution. And so here I'm flashing Rule 1, Rule 2, and Rule 3. And I'm going to go ahead and scroll down and flash Rule 4, Rule 5, and Rule 6. So once again, feel free to pause this video and take snapshots, or pause this video and write this stuff down on a piece of paper for your reference. All right, so let's go ahead and get started. And so in part 1 of this lecture video series for this specific topic, we learned how to predict whether or not the ions of an ionic compound will affect the pH of the solution. And if it did affect the pH of the solution, will it be more acidic, more basic, or will it stay neutral? Now, for number 1, it's going to ask 2 questions. We're first going to predict whether or not 0.125 molar of methyl ammonium chloride will affect the pH of the solution, and if so, will it be acidic, basic, or neutral? Next, we are going to take it one step further, and instead of just leaving off on that prediction, we are going to quantify the pH of that solution if the pKb for methylamine is 3.357. So we're going to go ahead and take a step back and visualize this whole process. So we're going to go ahead and take a beaker and fill it with water, and then we're going to stick this pH probe. And this pH probe is going to determine what the pH of the solution is. So if it's just pure water, let's just say it's 7.00. And then we are going to take our ionic compound. Here in this case, it's going to be methyl ammonium chloride. And then we're going to go ahead and place it in water. Now, when we put this compound in water, what's going to happen is that the ions are going to separate. Now, this is a more complex ionic compound than you guys are used to working with, right? There's a whole bunch of elements. And so how do you know which one's the cation, which one's the anion? And you guys can go ahead and derive that from the name. And so if you recall from your first semester general chemistry, chloride, the IDE ending is used to describe the anion in an ionic compound. And so therefore, everything before chloride, methyl ammonium in this case, is going to be the cation. And so when this compound separates, this is going to be the cation, and this is going to be the anion. So feel free to use that advice or trick, so to speak, to be able to differentiate what the cation is and the anion is. And so when we place that compound in water, it's going to dissolve. So we're going to go ahead and summarize everything in that picture in a chemical equation. So we have CH3, NH3, Cl. And when we place this compound in water, what we get is methylammonium. Methylammonium and chloride ion. And so remember that this chloride ion, if you look at the periodic table, it's under the halogens, and so therefore it has a fixed charge of -1. And so if you separate that chloride from methylammonium, then that methylammonium must have had a positive charge to begin with. And so both of these substances are going to be aqueous in state. So very similar to what we did in part 1 of this lecture video series for this topic, we're going to go ahead and address whether or not CH3, NH3, or chloride is going to affect the pH of the solution. And so let's go ahead and do the first product. And so we're going to ask ourselves, will it affect the pH? And so we're going to go ahead and scroll up, and we're going to look at our rules. And so remember, the ion that we're kind of looking for is CH3NH3. And so here is CH3NH3, a group 1A or group 2A metal. And if you answered no, then that's correct. And so since, I'm just going to copy this here, and then I'm going to erase this. So since methylammonium is not an alkali metal or an alkali earth metal, then therefore we cannot use Rule 1 to justify whether or not that ion is going to affect the pH. So let's go ahead and use Rule 2. Let's go ahead and look at Rule 2. Once again, we have CH3, NH3 plus. Okay. So that's the ion in question. And so we're going to, so looking at Rule 2, it's saying that the conjugate acid of a weak base can affect the pH of a solution. And so here, we first want to make sure that it fulfills the first part of this brief. And so is CH3, is methylammonium considered an acid just in general? And so if you guys are looking at the chemical formula, notice that there is a positive sign on NH3. So that lets us know that there's an extra proton that could possibly be ionized, thereby allowing methylammonium to be considered an acid. And so, long story short, it does fulfill this highlight. CH3NH3 is an acid. And the next thing that we're going to do is determine if its conjugate is a weak base. And so the conjugate of this conjugate acid, CH3NH3, is going to be CH3NH2. So remember, as you go from an acid to a base, you're going to lose one proton. And if you lose one proton, then the charge goes down by 1. So instead of writing +1, now it's 0, because we go down in value. And so if this is the weak base of the conjugate acid, CH3NH3+, we're going to go ahead and check whether or not this compound is going to be in our list of weak bases. And so we're going to go ahead and use this list to determine if CH3 NH2 is going to be a weak base or a strong base. And so looking at this rule, notice that the common strong bases have a group 1A metal or a group 2A metal that's complexed with a hydroxide, that's ionically bonded to a hydroxide. And so if you look at what we have currently, we have CH3NH2. And so the identity of this compound is not on the list of strong bases. And so therefore, it must be a weak base. Okay. And so hopefully you guys understand that logic, that train of thought. Basically, if it's not on the list that I flashed above, then it's going to be considered a weak base or a weak acid. And so since rule 2, since the compound, since both scenarios were kind of like checked off, right? So if it basically fulfilled that brief. Rule 2 is telling us that CH3NH3 or methyl ammonium can affect the pH of the solution. And so here we're going to answer yes. And we used rule 2 to kind of make that justification. All right. And so I'm going to go ahead and jump to chloride for now. We'll talk about the prediction a little bit later on. And so chloride is the next one in the chopping block, so to speak. And so I'm just going to go ahead and duplicate this question. Will chloride affect the pH of the solution? And so once again, I'm going to go all the way to the very top. And I'm going to go ahead and look at these rules. Rule 1, Rule 2, Rule 3, Rule 4, Rule 5. And I'm going to go ahead and erase some of these items that I wrote, just so there's no confusion between what I'm discussing now and what I previously discussed. All right, and so we're starting off with rule number 1. The ion in question is chloride. And so if you look at the periodic table, chloride is a group 7. And so therefore, we cannot use rule 1 to justify if chloride affects the pH of the solution or not. Okay. And once again, if we have chloride as our substance of focus, chloride, since it has a negative charge, it is not an acid. It's going to act as a base. And so since it doesn't fulfill the first part of this brief, rule 2, then therefore we cannot use rule 2 to determine if it affects the pH of the solution. And so if we look at rule 3, keeping chloride as the focus of our subject, Cl- does not have a high charge density. -1 is not very large, right? So it doesn't fulfill the first part to this, which is 3+ or more. Also, Cl- is not a transition metal, so we cannot use rule 3 to determine if Cl- affects the pH of the solution. All right, so let's go ahead and move on to rule 4. We're going to go ahead and determine whether or not Cl- fulfills this brief for rule 4. And so here in this case, is Cl- an anion? And the answer is yes. Cl- is an anion. Now, is Cl- found in a strong acid? Okay. And so I'm going to go ahead and take a scroll. I'm going to scroll the screen up. And here I have my list of common strong acids. and boom, I see Cl in our first compound. And so since Cl is an anion of a strong acid, in this case it's hydrochloric acid, then it fulfills the second part of that brief. And so I'm just going to go ahead and say yes. Okay. And so here in this case, since I have two yeses, then I can go ahead and use rule 2 to justify that Cl minus does not influence the pH of the solution. Okay. And so after all of that work, we finally concluded that no, Cl minus does not affect the pH of the solution, and we used rule 4 for our justification. And so since we have one yes, okay, we need to be able to predict how methyl ammonium is going to affect the pH of the solution. Okay, so how? And so if you guys look at the chemical equation, there's only 3 substances that's inside the solution. We have methyl ammonium, chloride, and water. And so methyl ammonium had already interacted with chloride, and if you notice, it's separated, and so therefore it probably won't react with it again. And so in this case, we're going to go ahead and compare water and ammonium, methyl ammonium. And so here we have methyl ammonium reacting with water. Okay. And so since there's a positive sign on this chemical formula, we can go ahead and treat it as if it's an acid. And it is an acid. It can fall under the Bronsted definition of an acid. The reason why is because it has an extra proton, and it's going to transfer that proton to an acceptor. In this case, it's water. And so technically water in this scenario is going to be our Bronsted base, while methyl ammonium is going to be our Bronsted acid. And so the result of this is going to be H3O plus and methylamine, CH3 and H2. So if you look at our products, remember that H3O plus is equivalent to a proton. And so since we're producing H plus in solution, we're increasing its concentration. And so since we increase the concentration of H plus in solution, the solution is going to be more acidic. And anything that's acidic will have a pH that's less than 7. And so going back to this diagram, if we place this ionic compound in solution, it is methyl ammonium that's going to increase the concentration of H plus, thereby making the solution more acidic. And so if the initial pH was 7, then after we added ammonium chloride or methyl ammonium chloride, the pH is going to decrease. Upon addition of this ionic compound. Okay. And so looking back at our original question, predict whether or not it's going to affect the pH of the solution, and the answer is yes, it will affect the pH of the solution, and the solution will be more acidic. Cool. Now let's go ahead and answer the second question. We're going to quantify the pH of the solution if the pKb for methylamine is 3.357. And we're going to assume that this takes place at 25 degrees Celsius. And so since we want to determine or quantify the pH of the solution, what we want to determine is the concentration of H plus at equilibrium. And so by determining the concentration of H plus at equilibrium, we can go ahead and figure out the pH of that solution. Now, to get us there, we basically need to understand or determine what the change is. And the change can be determined through your mass action expression or your equilibrium law. And to write a mass action expression, you need two more items. You need the ice table and you need a balanced chemical equation. And so we're going to be using concepts that we covered in prior lecture videos to answer this question. All right, and so we're going to go ahead and write, we're going to go ahead and figure out what the balanced chemical equation is. And we actually already did that. It's this equation right here. Okay, and so what we're going to do is we're going to rewrite that equation down below. So here we have CH3, NH3 plus. So remember that out of both those ions, it is only this specific ion, methylammonium, that's going to alter the pH of the solution. And so, let's see here. This is going to be our balanced chemical equation. So we're going to take this methylammonium, allow it to interact with water, and a proton is going to be transferred, so it's an acid-base reaction, to produce H3O plus and the conjugate base, which is methylamine. Okay, and if we balance the chemical equation, it's 1 to 1 to 1. We're just transferring one proton from one substance to another. We're not adding more of it. All right, now that we have a balanced chemical equation, we're going to go ahead and set up our ice table. And so our initial concentration is going to be 0.125 molar. Now, before I continue, I need to make sure that I have the correct physical states of matter. And so remember that water is going to be our solvent for any solution. And so it's always going to be designated as liquid to represent that it's a pure substance. And so what that allows us to do is that it reminds us that we don't actually need to incorporate water in our mass action expression. Okay, cool. And so let's talk about the change. The change can be either one of two items. It can be the initial concentration, or it can be minus X. And so here in this case, since methyl ammonium is not in our list of strong acids, then therefore we can conclude that this is a weak acid. So therefore the change is going to be minus 1x or minus X. And however much is consumed in the reaction, it's going to be produced as a product. I think I might have said that weird. So whatever was consumed in the reactants, products will be produced. So that's why we have a positive X and positive X. So we're creating hydronium and we're creating the conjugate base. So at equilibrium, we have 0.125 minus x, x, and x. Okay. And so the next part to our solution map was writing the mass action expression. And so the mass action expression is the ratio of products over reactants raised to their coefficient. And so here in this case is going to be H3O plus raised to the first power times this by CH3 NH2 raised to the first power, divide this by CH3 NH3 plus raised to the first power. Okay. The coefficients are 1, 1, 1, 1. Actually, I should not have circled this one. And so therefore, everything is raised to the first power. Now, all of this is going to equal to some type of equilibrium constant. And so we need to determine if this equilibrium constant is going to be Ka or Kb. And so if you look at our initial amount, so we have initially a weak acid. And so since we have only weak acid present in our initial state, then that means that we're discussing we're trying to describe the forward reaction. In other words, we're trying to determine the ionization of the acid. And so since we're talking about the ionization of the acid, this is going to be Ka and not Kb. Okay. And so we can just go ahead and plug everything in. So Ka is equal to, x times x over 0.125 minus x. We can go ahead and reduce this to Ka is equal to x squared over 0.125 minus x. So for us to solve this problem, determine what the value of x is, we need to figure out what Ka is. And so let's go ahead and read through the problem one last time. Let's see if they kind of gave us a value. And so here in this case, they told us that the pKb is 3.357. So they didn't tell us what the pKa is, but they told us that the pKb of its conjugate base, which is CH3NH2, is 3.357. And so you as a student really need to be cognizant of what equilibrium values you guys are plugging into these mass action expressions. Notice that this equation, since we have an initial concentration of a weak acid, we must describe everything in terms of Ka, or the ionization of the acid. And so since the problem gave us pKb, which was 3.357, we need to convert this into Kb. And converting it to Kb will allow us to determine its Ka. And so we're going to go ahead and to determine the Kb, we're going to take the base 10 of negative pKb. So that's one of the equations that we went over in prior videos. And so therefore Kb is equal to 10 to the negative 3.357. And since this is a p value, we have to identify the number of sig figs. So since there's 3 decimal places, if you plug this into your calculator, base 10 of negative 3.357, the answer needs to be reported in 4 sig figs. So you're probably going to have to round this up to 4.40 times 10 to the negative 4. And so to convert Kb into Ka, we're going to use the relationship Ka times Kb is equal to 1.008 times 10 to the negative 14 So remember, this value represents Kw at 25 degrees Celsius. And so if your temperature is not at 25 degrees Celsius, you'll just have to look up what the K value is and plug it in place of 1.008 times 10 to the negative 14, and then just solve the problem as you normally would. All right, and so we're going to go ahead and plug this value in here, and then we're going to go ahead and divide it to the other side. And so Ka is equal to 1.008 times 10 to the negative 14, divided by 4.40 times 10 to the negative 4. And if you plug that into your calculator, your Ka value is going to be 2.29 times 10 to the negative 11. And so now that you've determined your Ka, you're going to go ahead and plug that into your mass action expression. So 2.29 times 10 to the negative 11 is equal to x squared over 0.125 minus x. And so you don't really want to deal with quadratic equations. So we're going to see if we can ignore this minus x, if we can ignore the change in the denominator. And we're going to go ahead and ask ourselves, so to do that, we're going to go ahead and ask ourselves if the initial concentration is far, far greater than Ka times 100. And so the initial concentration is 0.125 molar. And the Ka, which is 2.29 times 10 to the negative 11, if you multiply that by 100, that's 2.29 times 10 to the negative 9. And so this statement is true. It's super true, right? 0.125 is far, 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 far greater than 2.29 times 10 to the negative 9. And so therefore, the actual change is going to be very, very small. So we can ignore it. So I'm going to say yes. And that allows us to cancel this guy out. That reduces our equation to 2.29 times 10 to the negative 11, which is equal to x squared over 0.125. And so this is clockwork at this point. We're going to multiply this to the other side. And that value is going to be 2.8625. And then there's just a whole bunch of numbers times this by 10 to the negative 12. And so since we want to keep only 3 sig figs, we're going to put a little mark above the 6 to remind us that we're only just going to keep up to that point. And so this is going to equal to x squared. So take the square root of both sides. And the value for x to the correct number of sig figs is 1.69 times 10 to the negative 6. And so we can see that if you look at the magnitude, it's times 10 to the negative 6. This is really, really low. And if our initial concentration is 0.125, we're not actually changing the initial concentration all too much. And so that allows us to validate our assumption that we can ignore this x. So if you plug in x into this part right here, 0.125 minus 1.6 times 10 to the negative 6, it's not going to change that answer a whole lot. It's not going to change that value a whole lot. So that justifies why we can ignore the x in the denominator. All right, so now that we've determined the value of x, that means that we're not done with this problem. We just determined one part to the ice table. And so remember, the question that we're trying to determine is the pH. We're trying to quantify the pH of the solution. So here we already predicted that it was going to be acidic, right? So it's going to be acidic. Now we want to know what that value is. So we actually, let me just, maybe a different color here. So we know it's going to be acidic. Now we want to determine the pH. And so we finished the mass action expression. We finished the balanced chemical equation, the ice table, mass action expression. Now we just need to determine the concentration of H plus so that we can get the pH. And so looking at this equation, we can determine the pH, the concentration of H plus by looking at the hydronium. The hydronium, if you recall from the past video, is equivalent to a proton. And so that's defined by X. And so therefore, the concentration of H plus, or hydronium, they're both equivalent, is going to equal to 1.69 times 10 to the negative 6 molar. And so to determine the pH, we're going to plug it into the formula, negative log of the concentration of H plus. We're going to take this number, wedge it right inside, plug it into our calculator, and the pH of that solution is going to be 5.772. Notice how there are 3 sig figs before we plugged it into the pH equation. And that means that we're going to have to report 3 decimal places. Okay. And so that's pretty much it. We've quantified the value of the pH, and it's going to be 5.772. And so if we look back at our drawing, right, and so notice that we predicted that the solution is going to be acidic, and now we've quantified the actual value as 5.772. Okay. So this is how you can kind of bridge these two topics that we've covered in the past lecture video series. And so I just wanted to bring that up just to showcase how to incorporate what we just learned here to that of what we learned in other lecture videos. All right, and so we're going to go ahead and work through a couple more problems. However, it's going to reflect a specific rule that we have not yet covered for determining whether or not, for predicting whether or not an ion of an ionic compound is going to affect the pH of the solution. And so let's look at number 2. For number 2, we are going to predict if adding ammonium fluoride will affect the pH of the solution. Will the solution be acidic, basic, or neutral? Okay. So these are that's a common question that we've been asking ourselves in this lecture video series as well as this. As well as the previous. So we have ammonium fluoride. Ammonium fluoride is NH4F. Okay. And so before we added ammonium fluoride, we filled this beaker with water, and we stuck a pH probe into this beaker of water, and let's just say it read 7.00. What we're going to determine is whether or not ammonium fluoride is going to affect or change this value significantly. All right, so let's go ahead and do that. All right, so when we have this ammonium fluoride, so we have ammonium fluoride, which is NH4F. We're going to place it in water, and when we do so, we get NH4 plus, and now since it's in water, it's going to be aqueous, and we have F minus, that's aqueous. So we're going to determine if ammonium is going to affect the pH of the solution. And so I'm going to just quickly jump into that final answer. I think we've done enough of these that you guys can figure out the process. And so NH4 plus, I'm going to look through my rules. Okay. So I really do need to erase this previous work because it doesn't apply to the current ion that we're looking at. Okay. And so NH4 plus, that is going to be, since it's positive charge, is going to be acidic. And so I'm going to go ahead and focus on rule number 2 first. And so NH4 plus, it is an acid. And so to make sure that we fulfill both parts to this brief, we're going to see if its conjugate is going to be a weak base. And so the conjugate of this conjugate acid, NH4, is going to be NH3. And so we're going to see if NH3 is in our list of strong bases. Okay? Because that's a list that you guys can memorize very quickly. And so if I scroll up even more, you'll see that for common strong bases, NH3 is not found in that list. And so therefore, it does confirm that NH3 is a weak base. Okay. And so it fulfills that brief. And so we're going to go ahead and say that NH4 plus is going to affect the pH, yes. And it's going to, so we're using rule 2 for that justification. So let's go ahead and look at F minus. We're going to determine if F minus affects the pH of the solution. So I'm going to scroll up. And I'm going to look at my rules. So rule 1 doesn't fit. F minus Rule 1 doesn't fit. F minus is not group 1 or group 2A. F minus is not an acid, it's a base. F minus is not a transition metal, and since it has a -1 charge, it's not considered a high charge density. And so let's look at rule number 4. Okay. F minus is an anion. However, is this anion found in our list of strong acids? And so it does fulfill this first part, but let's see if it fulfills the second. So if I scroll up, notice that F is not found in the list of common strong acids. And so therefore, it doesn't, it fails to fulfill the second part of that brief. So we cannot use rule 4 to make any type of conclusion. So let's look at rule number 5. And so F minus, since it has a negative charge, it can be considered as a base, more specifically a Lewis base. And we want to make sure that its conjugate, so if F minus is the conjugate base, its conjugate is going to be HF, right? So we're just converting that base to an acid. And so we're going to see if HF is a weak acid. And we can do so by looking at our list of strong acid. And if it's not on that list, then therefore HF is a weak acid. And so here, if you look, it's HF is not found on this list. Since it's not found on this list, HF is then considered a weak acid. And so both of those prerequisites have been checked off. So therefore, we fulfilled the brief for Rule 5. And if you look at the what Rule 5 says, is that if both of these are checked off, then that specific ion can affect the pH of the solution. And so let me scroll down to our original question. Can F minus affect the pH of the solution? Yes. And in this case, we are using Rule 5 for our justification. Now, in this scenario, this is a scenario that we actually have not come across, where both of our questions were answered by a yes and another yes. And so if you have both ions affecting the pH of the solution, then automatically you have to check out rule number 6. Okay. And so rule number 6 states that if both cation and anion, in this case NH4 plus and F minus, affect the pH of the solution, to predict whether or not it's going to be acidic, basic, or neutral, you have to compare its Ka and Kb. If one is greater than the other, then it's going to alter the pH by determining which one is much stronger. Okay. All right, so to for us to be able to determine how it affects the pH, we need to write full chemical equations. And so NH4 plus is going to interact with water, and F minus is going to interact with water. And so here, if we have NH4 plus, we're going to go ahead and put water as our second reactant. Now remember, this guy is going to act as our acid, and so one proton is going to be transferred from NH4 plus to H2O, forming H3O plus. And the remaining substance is going to be NH3. So that's the conjugate base. And so we're using the definition of Bronsted, the Bronsted definition. Okay, cool. And so for the second part, F minus, we're going to go ahead and react it with water. Okay. And we're reacting it with water because that's the only substance that these two ionic compounds can interact with. So I'm just going to put F minus at the bottom, and I'm going to react it with H2O. F minus is going to act as our Lewis base, and it's going to, take up one of these hydrogens. Okay. So the first product that we're going to get is HF, and the second product that we're going to get is OH minus. So if we take a hydrogen away from water, we just get OH. All right, cool. And so if you look at our product, notice that we form a hydronium and we form a hydroxide. So this hydronium is going to increase the concentration of H+. And this hydroxide is going to increase the concentration of OH. And so if you remember from, your the acid base, your fundamentals for acid base reactions, if you have H plus and OH minus, and if you have equal amounts of it, then they're both going to neutralize to form water. So H plus OH minus, I'll go ahead and write that down here, just off to the side. It's going to produce water. And if you only have water, then the pH of the solution is going to equal to 7, right? That's the assumption. However, these substances, NH4 plus and F minus, they have a specific strength to them. And so we have to look at their equilibrium values to determine whether or not the amount of H pluses or H3O pluses and OH minus that's being formed at equilibrium are actually equal to each other, or if one is a stronger acid, or determine whether one is stronger than the other. And so to do that, we have to compare their equilibrium constant values. So since NH4 is an acid, this forward reaction has to be representative of Ka. And if you look at the second chemical equation with F minus, since F minus is a base, we're describing, the forward reaction is describing the ionization of the base. And so we're going to go ahead and compare Ka and Kb, but we have to determine their actual values. So I'm going to go ahead and scroll up and look at some of the other stuff that this problem gave us. It told us that the Ka of ammonium is 5.60 times 10 to the negative 10. Okay, and so ammonium is NH4 plus. If you look at the first equation that we wrote, we have NH4 plus in our reactant, and the Ka value, according to the given, is going to be 5.60 times 10 to the negative 10. Okay. So this is the relative strength of ammonium as an acid. And so we're going to go ahead and do the same thing for F minus. And so let's go ahead and look at the second part to this. It turns out that the Ka of hydrofluoric acid is 7.20 times 10 to the negative 4. And so hydrofluoric acid is HF, right? So this is describing the ionization of HF. But that's not what we have here on our reactant side. We have F minus. And so before we can plug in a value for Kb, what we actually have to do is convert Ka into Kb to represent that, to represent its equilibrium, its ionization constant for fluoride, or F minus. Okay. And so since the given value for Ka is 7.20 times 10 to the negative 4, we want to make sure that the K value that we're using is reflective of the actual chemical reaction that's occurring in solution. And so we're going to use a relationship, Ka times Kb is equal to 1.008 times 10 to the negative 14. We're going to assume that we're at 25 degrees Celsius, and this is going to represent Kw. And so we're going to go ahead and plug this number into Ka, and to solve for Kb, we're just going to go ahead and divide it to the other side, so that we get a Kb value of 1.008 times 10 to the negative 14. And so if you guys didn't catch those steps, I encourage you to watch some of my previous videos because I showed my work there. But just think about this algebraically. We're going to plug in the value to where it's located, and since the operation is a multiplication, to move it to the opposite side, we'll just have to do the opposite operation, which in this case is going to be a division. And so we're going to divide 7.20 times 10 to the negative 4. And so the Kb value is going to be 1.40 times 10 to the negative 11. And so now that we have that value solved, we're going to go ahead and write that above the arrow. And so we have 1.40 times 10 to the negative 11. So now that we have all values of the ionization constants representing the correct values, and so we're expressing in the forward direction, we're now going to use these values to compare their relative strength. And so the relative strength of NH4 to produce H plus is 5.60 times 10 to the negative 10, while the relative strength of F minus acting as a base to produce OH minus is 1.40 times 10 to the negative 11. Here in this case, negative 10 is closer to 0 than negative 11. And therefore, Ka is greater than Kb. And so if Ka is greater than Kb, then what's happening in solution is that more NH4 plus is ionizing to produce more H plus compared to F minus, ionizing to produce OH minus. So we're producing more H pluses than OH minuses. Okay. And so if we have a greater amount of H plus than OH minus in solution, so to speak, then we can conclude that this solution, so overall, the solution will be acidic because there are more H pluses than there are OH minuses, and therefore we should expect a lower pH value. Okay. And so hopefully that makes sense. This Ka Kb relationship, I'm actually grabbing that from Rule 6, right? And so it's this part that's being fulfilled. Okay. So let's go ahead and do one more example just to kind of showcase, Rule 6. Okay. And so we're going to predict if adding methyl ammonium azide, which is CH3NH3N3, will affect the pH of the solution. If so, will the solution be acidic, basic, or neutral? And so they also gave us some pK values. So pKb of methylamine is that value. pKa of hydrozoic acid is 4.720. And so once again, visually speaking, we're going to take a beaker, we're going to fill it with water, and we're going to stick a pH probe, and the pH meter is going to read that this solution is 7.0. Then we're going to take this ionic compound, we're going to place it in solution, and we're going to ask ourselves whether or not that pH will change or stay the same. Okay. And so we're going to summarize what's going on in this image by writing a chemical equation. And so here we have CH3, NH3, N3. We're going to place that in water. And in this instance, once again, you guys can kind of implement that technique that I showed you guys later. If you don't know what's the cation, what's the anion, look at the name. And so IDE is found azide. And so the azide molecule in this case is N3. Okay, so we're going to go ahead and cut it off. So hopefully you guys were introduced with the polyatomic azide in your first semester general chemistry. It's common use. So sodium azide is found in airbags, and so if you if you added a spark or you added energy, the sodium azide is going to decompose to produce N2 gas, and that's what quickly fills up the airbags inside your car when you get into a car accident. Hopefully you guys won't ever have to experience that. And so here we just have CH3, NH3, and when we separate it, it's going to have a positive charge, and the azide is going to have a negative charge. Okay. And so we're going to go ahead and determine whether or not methyl ammonium is going to affect the pH of the solution. Then we're going to go ahead and use our rules. And so we kind of did it earlier. So let's go ahead and look at rule 2. So CH3, NH3 plus, that's going to be our acid. Okay. And the conjugate, so that's going to be our conjugate acid, and the conjugate base is CH3, NH2. These are both conjugate acid-base pairs. And so since CH3NH3 methyl ammonium is an acid, it fulfills that part of rule 2, and we just need to make sure that its conjugate base is a weak base. And so if you look at the rules, or I'm sorry, if you look at the list of common strong bases, that compound that we just wrote down is not found. Okay. So therefore, it is a weak base. Cool. And so the other compound, so let me just go ahead and write that down here. So does methyl ammonium affect the pH? The answer is yes. Okay. And we used rule 2 for our justification. Next, we're going to look at N3 minus. So will N3 minus affect the pH? And so we're going to go ahead and scroll up, look at all these different rules. Okay. And so I'm going to look at rule 5. So rule 5 here, it's going to be, so we have, hold on, where are we? Oh, N3, that's right. So for azide is a base. Okay. And so if we convert it into its conjugate, which is HN3, we want to determine if HN3 is a weak acid. And so if I scroll all the way up, notice that HN3 is not found in my list of common strong acids. And so therefore, it's most likely a weak acid. So it fulfills this part, and if you read on in rule 5, it does affect the pH of the solution. If you look at rule 2, if you check off this part and this part, it does affect the pH of the solution. So this is another situation in which both ions can affect the pH of the solution. And when this occurs, once you get yes and a yes, you have to look at rule 6. And rule 6 basically states that we have to look at their Kas and Kbs and determine which one is higher and lower. And if one of the K values is much higher than the other, then it's either going to be acidic or basic. If they're equal to each other, then the pH is equal to 7. Now, to determine whether or not the Kas and Kbs, now to determine if whether or not one of the Kas is, or one of the K values is higher than the other, we are going to look at, we have to write down the chemical reactions. And so here in this case, we have methyl ammonium. It's going to react with water. We have this azide, and it's also going to react with water. Okay. So you have these two ions, methyl ammonium reacting with water. And since it's a positive sign, we know that this is going to be an acid. And acids donate protons, and so therefore one of our products is going to be H3O+. So it's going to go ahead and donate one positive charge, or one proton, to water, creating H3O+. And the result of that is methyl amine. So we reduce the number of hydrogens from 3 to 2. And so since this is describing the ionization of an acid, the forward reaction must be in terms of Ka. And so we're going to go ahead and take a look at our given value. And so it looks like they gave us a pKb, and it's that of methylamine, and it's 3.357. So methylamine, or CH3NH2, is not the same as CH3NH3. Okay. And so this right here is methylamine, and they gave us the pKb of this compound. And so we're trying to go in the forward direction because we want to ionize our acid. And so therefore, we need to convert this value into Ka. And so since the pKb is equal to 3.357, we can determine the Kb if we take that value and plug it into the equation. And so here in this case, base 10 of negative 3.357 is going to give me the Kb value. And that's going to be 4.40 times 10 to the negative 4. And so now that I have my value for Kb, I'm going to use the relationship Ka times Kb is equal to Kw. And if I move this term around, because remember, I want to solve for Ka. And so Ka is equal to Kw over Kb, or 1.008 times 10 to the negative 14 over 4.40 times 10 to the negative 4. If I divide those two values, that's going to give me a Ka value of 2.29 times 10 to the negative 11. And so I'm going to go ahead and just kind of put here that I have a Ka value of 2.29 times 10 to the negative 11. All right, so that fulfills this reactant, or this first ion. So we need to do the same process for N3-. And so N3-, it's only going to react with water. That's the only other substance in the solution that's present. And so we have N3- plus H2O. And so N3- is a base, is a negative charge, Lewis base. And so bases, they extract a hydrogen from water. And if you take one hydrogen from water, you're just left with OH-. and that hydrogen goes back to N3. And so this is going to be HN3. Okay. And so since my reactant is a base, I'm describing in the forward direction the ionization of my base. In this case, it's going to represent Kb. And so if I look at my given values, so this is the original question, they gave us the pKa of hydrozoic acid, which in this case is 4.720. And so if you look at the structure, hydrozoic acid, HN3, that's actually not the reactant. That is the product. And so they're telling me that the pKa of HN3 is going to be 4.720. And so I cannot use this value as is. I have to convert it to Kb. And so to perform this conversion, I'm going to take pKa and convert it to Ka. And then from Ka, I'm going to convert it to Kb. And so what allows me to go from pKa to Ka is if I take the base 10 of negative pKa, so that's going to be 4.720. And so if you plug this into your calculator, the value of Ka is going to be 1.91 times 10 to the negative 5. And so now that you have your Ka, you can convert it to Kb using Kw as an intermediate. So you can go ahead and convert Ka to Kb by using Kw. So Ka times Kb is equal to Kw. Since we're solving for Kb, we're going to divide it Ka to the other side. So Kb is equal to Kw over Ka. So Kw is 1.008 times 10 to the negative 14. Divide this by Ka, that's 1.91 times 10 to the negative 5. And so the value for Kb is going to equal to 5.29 times 10 to the negative 10. And so I'm going to go ahead and plug that number into here. So 5.29 times 10 to the negative 10. Once again, these equilibrium constant values with respect to this topic is giving me like a relative, it's a measure of the relative strength of the ionizations of the base and the acid. And so to summarize, the relative strength of the ionization of the acid is 2.29 times 10 to the negative 11. The strength of the ionization of the base is going to be 5.29 times 10 to the negative 10. So I'm going to kind of zoom out here so you can see both values. And so which of the two do you think is going to be stronger? So if you had said Kb, then you're correct. Since the value of Kb is times 10 to the negative 10, that is much greater. That is greater than times 10 to the negative 11. And so in this scenario, Kb, I'm going to zoom in here, is greater than Ka. Okay, so 5.29 is greater, times 10 to the negative 10, is greater than, 2.29? 2.29 times 10 to the negative 11. So looking at the relative strength of the ionization of the base and the acid, it looks like the ionization of the base is much larger than the ionization of the acid. And so therefore, more OH minus will be produced in solution. And so if more OH minus, And so we can kind of see that here. Notice how we're producing the OH minus. If more OH minus is being produced, then we're going to, our solution is going to be more basic, and the pH of the solution should increase. So this is our prediction. Okay. And so if we're looking at this diagram, when we add methyl ammonium azide, it's the azide that will increase the pH of the solution. So it's no longer going to be 7, it's going to be greater than 7. And so we need more information to quantify it, but at this point in time, the main purpose is for you guys to make those predictions. So that's pretty much it for this lecture video. Hopefully you guys understand how to use rule number 6 to determine if you have two ions of an ionic salt that can affect the pH, like both of them can affect the pH of the solution. And so if both of them can affect the pH of the solution, then you will have to use the correct equilibrium values and compare them to see which ionization constant is much greater than the other. All right, so that's pretty much it for this topic. We're moving on to the next section of this chapter, which is polyprotic acids and polyprotic bases. All right, see you in a bit.